Welcome to the third phase of the UAM Feasibility Study webinar. In this third phase, our focus will be on the built environment. So you may recall that our second webinar focused on collecting valuable insights from the community through the second phase survey, and we received an excellent response to the survey. So we're using this data to understand the communities and the stakeholders' preferences and opinions regarding various aspects of UAM land use specifications. In this third phase, we will present the proposed built environment for the Vertiport location, and we aim to gather additional data from the third survey and applying these results along with other factors that we need to take into consideration for our UAM feasibility study. After presenting the survey, we are going to introduce you to terminal systems, runway orientation, pavement, vertiport drainage, vertiport security, and energy requirements. As we progress towards a comprehensive feasibility study, we will lay the foundation for a sustainable and efficient UAM system in Chicago. So let's begin the third UAM feasibility study webinar. I'm Sandra Fermenton, CEO at eVertiSKY, and I will be joined by Stephen Philpott, our CTO. Next. So let's give a look to the survey results. Regarding the interest in UAM cargo and passenger services, it is interesting to see that 36% are property owners or developers. And this may also suggest that they see potential benefits in incorporating UAM services into their development plans, which may indicate a growing interest in investing in this emerging industry. And it is not surprising that efficiency and speed are considered the most important factor when planning a UAM infrastructure, as time saving and quick transportation are often the main selling points of UAM services. However, as seen in our previous phases, environmental sustainability is also highly valued by responders. Here, the preference for large and heavy goods as the best type of cargo suited for UAM transportation is really interesting, as it may suggest a potential market for UAM services in industries such as logistics and freight. And another additional aspect is the willingness to travel more than 10 miles to reach a UAM vertiport is really promising, as it indicates a level of demand and interest in UAM activation. Next, please. Regarding the interest in UAM cargo and passenger services, it is also interesting to consider the access. So this slide highlights the need for careful consideration when designing and implementing regulations for UAM services. And here, the majority of responders not supporting time restriction on UAM vehicles access to the facility is a positive sign for the potential of UAM services to offer flexible and convenient transportation options. Also, we can see here that the majority preference for designated parking areas for UAM vehicles suggests that responders see that need for organized and efficient management of these facilities. And also, of course, the use of access control systems to monitor access to the facility is a positive sign for safety and security. And it is important to ensure that these systems are designed and implemented to balance safety concerns with the need for convenient and efficient access. Here we can see that the positive response to having a designated parking area for users' vehicles near the vertiport highlights the importance of considering the needs of users and also ensuring that these facilities are designed to provide convenient and efficient access to the UAM-enabled area. Here we can see also the strong preference for a separate entrance for emergency vehicles. It is really important consideration for safety and security, ensuring that emergency responders have quick and efficient access to UAM facilities, and this can be critical in emergency situations. Here we can see the survey provided two options for aircraft parking: a stopover parking location for eVTOL aircraft versus one that only allows pass-through flights. The division, in opinion, highlights the need for careful consideration of the needs of different operators and the potential impact of UAM services on surrounding communities. We can also here see that the preference for making eVTOL aircraft parking available to any aircraft is a positive sign for competition and innovation in the industry, but is also fundamental to ensure that regulations are in place to promote safety and efficient use of these facilities. We can also here give a look again to the slide. We can see the preference for charging infrastructure for eVTOL aircraft to be provided by UAM location. This highlights the potential benefit of centralized management of these facilities. And finally, we can also here see that the strong preference for UAM vehicles to access the facility via air only is not surprising, of course, but this is really important to consider the potential impact of noise pollution and safety concerns associated with air traffic. And then access control system to monitor access to the facility is also a positive sign for safety and security. Next, please. Thank you. In this slide, when it comes to first response, according to the survey, the responders selected preference for the first response team to arrive at the vertiport within 10 minutes in case of an emergency. And this also highlights the importance of safety and prompt response times. However, 40% of responders allowed for a response time up to 20 minutes. There is also a strong preference for the first response team to have their own dedicated flight paths to access the vertiport, and it is really an important consideration. Another aspect is the preference for first response team to participate in drills or exercises to prepare for UAM-related emergencies on a quarterly basis, and this highlights the need for ongoing training and preparation. This is another important aspect, that it's a strong relationship and communication between the first response team and also the UAM operators and vertiport management, which is really critical consideration for ensuring effective emergency response. When it comes to the public sentiment, here we can see the preference for UAM services to be inclusive and accessible to all. And this is really important for ensuring that these services are designed and implemented in a way that considers the needs of all users. And then the relatively low level of concern about the potential increase in air traffic due to the UAM operations in this location is really a positive sign for the potential success of UAM services in the selected area. And finally, the strong preference for UAM services to have a positive impact on existing transportation infrastructure in this location. And this highlights the potential benefits of UAM services to increase the value and economic development for the selected location. When it comes to geographical consideration, here, according to the survey, the proximity of the vertiport location to downtown area highlights the potential demand for UAM services in urban areas, maximizing efficiency and convenience for all users. And the strong preference for economic development in the surrounding area near the Vertiport location highlights the potential economic benefits of UAM services for local communities. Thank you. I'm going to hand it over to Steve.
Thank you very much, Sandra. So as Sandra was saying, we've looked at various aspects of designing the vertiport, the mock vertiport that would be located at 6200 South State Street in Chicago. And the requirements that we gathered up to this point were driven by the vision that was really driven by the respondents' data that suggested what the land should be used for. So we've gone through vision, land selection, and land use specification based on those drivers. Now we're going to look at the components of the actual built environment based on the vision and all the other elements that go in there. Now, the study is focused on analyzing the feasibility of implementing urban air mobility, not just the vertiport itself. The built environment and the design of the vertiport are crucial elements to this analysis. However, it's not just the building, it's not just that area that we look at, and I think you'll be able to see some of that as we talk about some of the elements that are important to this process. So let's talk about the terminal system. One thing I think we should probably express up front is that we looked at, of course, the FAA engineering brief for vertiports 105, as well as some documentation out of EASA and some of the other aviation validation bodies out there working in urban air mobility. And we found that there are some existing practices and infrastructure that can be adopted from traditional aviation. However, this may be a time where planners can really begin to reimagine processes, technologies, and experiences. When we talked about what the general requirement would be for the built environment, we lean heavily on it being climate resilient. It's very important according to the community sentiment, as well as the general nature of the industry. Aviation is a very carbon inefficient operation, and to move to urban air mobility means that you'll be able to flip what was the transportation industry's negative effect on the environment to a positive effect. So we want to look at these particular tenets when we're designing at a high level, but we want to bring in those materials, those processes, those technologies to make these things possible. So within our terminal system, we look at the access, processing, flight interface systems that actually carry out the components that will provide an efficient processing of passengers, as well as the need to accommodate these new aircraft, excuse me. So the access component of the urban air mobility passenger terminal will focus on several key areas to ensure a seamless and enjoyable experience for the passenger. This particular location is in its requirements based on the vision, capable of both cargo and passenger transportation. Of course, the passenger experience is going to be tantamount to great efficiencies and revenues. So we want to look at the passenger check-in experience first. What's that like? Well, let's reimagine it. Let's make it well organized and efficient and essential to the overall operation. The passenger check-in should be super seamless. There should be designated check-in counters, self-service kiosks, other technologies that make it simple, but we shouldn't just mirror the existing passenger processes of traditional aviation. We should again reimagine that. And that includes the passenger holding area. Are we taking passengers at this location in a just-in-time nature where they're traveling back and forth from work and they don't have much baggage, or is this a centralized location to travel to an airport or much further regional air mobility destination? Also, the boarding gate should be strategically located to facilitate efficient passenger flow and minimize the walking distances. There needs to be clear signage and gate numbering to ensure the passengers can easily navigate to their designated boarding areas without ending up on the tarmac and impeding operations. The other thing is that many of the vertiport plans that are underway are looking at those vertiports to be facilities that really engage the customer experience. So there may be the opportunity for retail and food services. And we're talking a variety of food service options within the terminal to cater to passengers' needs and enhance their overall experience. So you may have shops selling travel essentials or gift items or local products or things that people would need going back and forth in a commuter transit model. The processing side of the system, of course, is going to focus on the baggage holding / security. Really, we don't know just yet what the typical passenger's baggage requirement is going to be, but we will have to build in a design of an area that can accommodate certain levels of baggage volume, the ability to sort through that volume and also screen that baggage. So what unique process can we tailor to meet the specific demands of UAM? What processes exist today that we can adopt? And then what technologies are available that we can really implement to manage the capacity, the anticipated capacity, the various sorting mechanisms required for proper allocation so bags don't get lost on respective flights, and incorporating certain screening procedures that maintain the security, allow for a customer to maintain their integrity during the experience, but also more importantly, prevent the transportation of prohibited items. Now, security, of course, everyone thinks about security in terms of the passenger being a possible insecure point, but we really want to look at securing the safety of the passengers, the vertiport personnel. Those are priorities, but everything get involved in that ecosystem needs to be accounted for. Specific to the area where we're processing passengers, we want to make sure that the security process has a very short turnaround times. Given that there are going to be more transit hops, basically more trips than there would be at a regular airport, you want to develop a security process that allows for the quick and efficient screening of passengers and their baggage, quite simply. And then with the aircraft, the aircraft themselves in that area, we have to look at measures that help us secure that aircraft, that area, as well as the specific unique nature of various types of aircraft. So we have to look at all of those aspects in terms of security. The flight interface is really the component of the terminal that ensures the operational aspect, the coordination of the passenger terminal and all other key elements, including emergency management, information, communication technology, maintenance and operations. So it's the brain of the operation. And then it's connected to those emergency management systems. And as in every transit hub, the emergency management systems has to look at the standardization of the procedures and the facilities that we would require to handle a number of types of emergencies that may occur within and around the vertiport and the terminal area itself. So the design of the emergency management system will need to cater to that variety of unique requirements. And when I say unique requirements, there are some standard emergencies that will occur, And there are some emergencies that may be very unique to the operation of UAM aircraft or the operation on the ground itself. And that needs to consider rapid evacuation. So the ability to facilitate swift and orderly movement of passengers. So how does that happen? What's the standard operational procedure? What are the physical movement and the personnel required to make that happen? What are the fire suppression systems? We have to implement a fire suppression system specifically designed for UAM terminals. When you think about it, there will be the standards of traditional firefighting, but our aircraft on that property, on that parcel, they're going to be electric dependent or electricity dependent, and electric batteries don't do well in fires. For whatever will cause that fire, putting them out is a completely different process than a standard fire. So we have to prepare for that. And then of course you need medical facilities that establish some sort of on-site availability, some access to personnel that will handle medical emergencies and provide prompt assistance to passengers and staff. Is this an on-site person? Is this an on-site facility? Is this access to a facility that is managed by the local municipality or a private partnership? These are things that need to be considered. And then coordination with other vertiports, the other vertiports that may be within maximum reach, or I'm sorry, the maximum flight distance of aircraft may have, may need us to design response protocols that enable seamless communication and coordination between our vertiports when those emergencies that may be coming inbound from another vertiport occurs. So designing the information and communication technology system for UAM operation has a number of other components really just meant to interface with the passenger information displays that will move the passengers. Flight information displays are one good example. Public address systems, other digital signage, and any maintenance and operations personnel that need to be aware of various things. And that's within the terminal. The terminal infrastructure must be maintained. You must implement a regular maintenance and repair schedule to ensure the terminal infrastructure remains in optimal condition. Now, why does that apply to looking at the built environment? There are going to be various materials and various processes that will be new. We won't know the shelf life of them. We won't know the durability of them, or they will require high maintenance. So we need to look at all of those things when we consider the actual terminal infrastructure and maintenance, the operations management of the terminal, and coordination within the civil airspace. So the flight interface is a pretty integral part of the process. So we understand that our area, our Chicago Vertiport study is looking at an area that is roughly 8 miles west of a major airport, Midway Airport here in Chicago. And so we want and need and are required to, and while there aren't any hard suggestions on how this should be done according to the regulators just yet, we're fairly certain that these fundamentals will still apply. So in setting up the runway orientation for our location, we looked at the core aspects that are often, if not always, considered when planning an airport itself. We don't have runways, but we certainly have taxiways, and we certainly have entrance and exit zones or departure and approach lanes into and out of the airport. So these components that are on the screen here, there's no reason to really read them to you, are the baseline components of ensuring that we can start the built environment with an optimal integration and alignment into the airspace for safe operation of the aircraft. We considered the proper taxiway and taxi line orientation in terms of also facilitating passengers transferring from the terminal to an aircraft, from an aircraft to a terminal, from an aircraft that's not typical to the terminal, but how they operate within our environment is what we needed to consider. And we also talk about a couple of other things in terms of the exit taxiway and geometry, taxiway designations, taxi signs. And so these are the things that we consider. Let's talk about just a little bit more because they're a bit important. So we talk about the FATO configuration. In civil aviation, you have various designations of the configuration of the airport, and it's based on how it's seen from the air, essentially. But the requirements are almost all the same. And so what we looked to do was find a standard configuration that will incorporate the principles of civil aviation into the ground space for operation. So where we said we have 3 FATOs, which would be passenger dedicated, and then 1 FATO, which would be probably cargo dedicated. With multiple FATO areas for simultaneous operations, we need a design that can increase or manage capacity and be efficient while accommodating the ground necessity of those aircraft. So do we have space for you to land right now? Do we have space for aircraft to move so you can land? Do we have corridors that are dedicated for a safe and efficient flow in and out of the area, especially within a city like Chicago? It's a dense urban environment. So establishing these standards up front, clearly defining ingress and egress to this built environment, this configuration that we're considering minimizes potential conflict. So what we did was we decided on what we call a FATO Z, So in civil aviation, you have an open W. FATO Z, again, when viewed from above, would give you that Z look, would allow for multiple approaches and spacing. So let's take a look at what that looks like. So the FATO Z, we've got our 3, and we don't know where the terminal is going to be. We don't know where the FATOs are going to be laid out, but in terms of our square footage, our approach, and even our wind rows, our alignment with the airport and airspace, we know that we can place these in a way to allow for movement of the aircraft, people, and the staff. So the wind rows, let's talk about that. So when we talk about a rose, it's the same as the compass rose for you navigators, aviators, all you guys out there. The face of a compass is called the rose, compass rose. So when we talk about a wind rose, it's essentially a compass that is locked in on magnetic north, so that all runways at airports have a standard by which they can operate for wind and a number of other things. The wind rows, even with UAM, it's essential to understand the significance of wind patterns in determining the optimal orientation of the FATOs. So the wind rows gives us that direction, and then we can spec out additional information to get a geographical representation of wind speed and direction data for that location. Initially, as planners, we can do this analysis to optimize the orientation of the FATO, excuse me, for safety as well as efficiency. And when we talk about efficiency, we're talking about the ability to line up those approach and departures according to the FATO, according to the wind, so that you can shrink the sequence between aircraft. That means more aircraft on the ground, more revenue through that vertiport. So aligning that windrows is crucial for UAM planning in the beginning, because you will determine that optimal orientation. For anyone that needs more information about the very exciting windrows, I'm sure you can look it up, but the windrows really is our our baseline for setting the alignment of the taxiway and taxi lane orientation. So at 62nd or 6200 South State, this is a very busy location. There is a railway, a very busy railway, cargo railway just next to it. And there's a hugely busy highway or interstate, as well as a mass transit system. And then a bus route system along 4 really busy streets. So in looking at the baseline stuff we need to know for taxiway and taxi lane orientation, we're going to look at the FADOs. Excuse me, the FADOs. So what are we're going to call them pads for a second. So what are the dimensions of those pads, and how far do they need to be separated was determined by the FADO-Z, right? Those proper dimensions and spacing, those are crucial. So secondly, we have to have that transition area, and those transition areas are really the taxiways and the taxi lanes, and we orient those taxi lanes for adequate separation in those static areas, so that the vertiport is minimized, or we can mitigate the potential for collision. And we can also streamline operations because of this predictability on the ground. The other thing we are going to really delve into is maintaining a proper line of sight and adequate vertical clearance. So that, for example, on the ground, if I am a operator on the ground and there's an air taxi coming in and it's hovering, there must be a transition point where that aircraft can now visually see that vertiport, the aircraft can see the vertiport, or the aircraft can sense the vertiport. Either way, the infrastructure must be clear, or it must provide the aircraft or the pilot the sufficient visibility to avoid obstacles and other aircraft while in that particular approach and hover. So it's important on the ground that we create that proper line of sight when considering the placement of built environment assets. Now, the ground movement coordination on the ground is necessary for the aircraft that require repositioning. So if you're coming from the cargo area to one of the departure FADOs, well, this must be a standard, and this movement must be carefully planned in advance based on the experience and the business model of that vertiport. So if you can do that, you can truly coordinate your processes and your operations to minimize conflict between the aircraft and the ground operations. And if you've ever been to O'Hare Airport, you know that's always a fun operation to watch. The ground aircraft and the ground staff working. So the placement of the vertiport facility will minimize that conflict. We'll also need to consider the fleet mix. So will we have a mix of Joby aircraft with EHang aircraft? What are the speeds of these aircraft? What are the hover characteristics when it comes to the prevailing wind patterns? Things like that, we have to design those into the particular taxiway and taxi lane orientation, because the placement of where they land and take off will make a difference based on their aircraft characteristics. One of the biggest things you hear right now in all of the industry circles that talk about planning vertiports is the connection to other vertiport hubs, or I'm sorry, connection to other transportation hubs. And so will our taxiways and taxi lanes need to line up with those other transportation hubs. That remains to be seen. That really remains to be seen. It's going to be the number of transactions that may occur along a certain route that is in close proximity to a transportation hub, or it may be that a transportation hub becomes a destination vertiport hub that now needs a route designed into it, and that your vertiport lane or taxi lane, a signage now must line up to it in various ways. That's taking a little further than we need to, but if there's another vertiport out there, can we connect to it? The last thing is that everybody cares about noise. Everybody cares about noise. Is there a way that the infrastructure can be designed to minimize the noise pollution during approach and takeoff? Is there a way that noise can be mitigated by materials as aircraft idle or in maintenance? So these are all the things that we are looking at to make sure that the Chicago location is amazing. Okay. Pardon me. Computer's running slow. There we go. Okay. So here's where we are now. We are building the report based on the inputs, the requirements that we have. So obviously some of these requirements have caused us to begin to tinker into the actual study outcomes. And one of the things we looked at were the inbound integration of flights and the outbound integration of flights. And the simplest way to put this is that the vertiport will require the taxiways to provide access to the runway in a way that integrates with, well, it considers their size and weight of the aircraft. So we have to have maximum space, tip to tip, nose to tail. But we also need to be able to ensure that when they're approaching and landing, that our built environment, again, on approach and coming in, adhere to the safety that we'll require. And one key factor that everyone talks about is a way to minimize the impact of any prevailing winds. So doing that initial study should help to reduce some conflicts. But most of all, it will help operators and manufacturers understand what additional considerations they need to make these aircraft a standard in these particular locations. I think I lost my voice. There we go. So we have inbound integration with the ground space. We have outbound integration with the ground space that we have to design into. In designing the ground movement paths, given the space, as well as the size of the aircraft, curvature plays an essential role. So we take into account the turning radius of the aircraft, the potential aircraft that will be there. Now, we haven't selected the aircraft just yet. We have some ideas. We have a short list, but we still need to get more characteristics from the manufacturers to determine which ones we will recommend in our final report. But the planners, once they get this data, can ensure a safe and efficient maneuvering around the entire vertiport. You think about the intersection angles, those places where aircraft will come closely together or aircraft and people may come close together. We have to design in various protocols and processes to minimize the risk of collision and facilitate that efficient movement. And of course, we look at visibility because it's a crucial aspect all the way around in aviation. We want the pilots to be able to see, we want the staff to be able to see, we want the aircraft to be able to see, quite frankly. And then lastly, we want adequate clearance available or made available through those taxiways and the shapes that we determine to be paths within the surrounding infrastructure. In our case, we explored the topic of taxi geometry, the actual shapes that we would use. The FAA may come down with more concrete recommendations. However, we're taking a cue from existing helicopter vertiports, right? But helicopter vertiports don't have that granular design for high traffic, if you will, or even taxiing amongst various size aircraft in close proximity. So over the next 2 years, where we say there's some things that are basic that probably won't be changed, these things may change. The actual geometry for the vertiport, we think the FAA will have more standardization come down the pike, and probably with industry input. Now, although the operations don't require traditional taxiways like an airport, the standard identification and organization systems that are already available in aviation for ground movement, paths, the infrastructure, are probably the best paths to mirror in planning safety and efficiency in terms of the taxiway designations. So for ground movement paths, there are already standard naming conventions. Some may need to be modified, but specific to communication and coordination among between the aircraft, the ground crew, the vertiport management team. We need to have clear and unique designations. That also, of course, applies to the passenger boarding area, the passenger boarding process, the passenger amenities. All of those things should be within close proximity of when that person gets off of their flight. The other thing we talked about very heavily, because this is the most important piece, in terms of eVertiSKY's approach to building urban air mobility ecosystems, the impact of the energy requirement on not just the vertiport, but on the area in which it will be deployed could be tremendous. And we'll talk about that a little more towards the end of this presentation. And I'm not going to go into it much now, but the charging requirement is probably going to be a huge concern. And that's really driven by the type of aircraft that you will select to be your standard operator or even allowed in your vertiport. So the maintenance and charging areas, they can benefit from specific designations rather, but it's very important to choose what type of energy infrastructure you're going to place. Again, this is a place where you can maybe implement some new approaches, because it's going to be, the energy requirement is going to be expensive, it's going to be complex, and it's going to either be a plus or a minus for that area of the grid, of the municipal grid. So you have to look at that. That took it a little further away from taxiway designations, but that'll happen from time to time. So the taxiway designations that we're talking about right now really are the communication standards within the vertiport operation. That's really what we're trying to say. Those standard designations speak to all of the moving aspects, the ground crew, the people, the management team, even people that see this facility from the outside. The taxiway designation is going to be very important. The signs, very same thing. So now we've designated what this area is. What are the signs that we're going to put up? Again, in the aviation regulatory side of the house, there are tons of regulations, certifications, and documents that will talk about types of signs to be put up. Now, some of those signs may be slightly different for UAM, but the possible adaptations of the traditional aviation segment are to look at the mandatory instruction signs. So where do I have to go? Which direction is this? Very mandatory stuff, well lit, easy to see. location signs. Where am I? Where do I have to go? Direction signs. If you're going this way, you need to go this way. Destination signs. All the standard signs that you see today in an airport must be considered, not replicated, but considered in creating the signs for your taxiway to make it to make your vertiport efficient. To be quite truly, I mean, all of the signs that are available will convey the most important information that will be the most important information for both safety and for revenue. Now, this is the most exciting piece ever. It's really not even close, but the pavement design should account for the unique characteristics of the operation. Everything does, right? But when we talk about takeoff and landing, noise, vibration, electric charging, and even the regulations that come down the pike, we have to think about pavement. Because why? Well, we've done it in civil aviation forever, and we know pavement is important. So let's talk about pavement. Pavement requirements are kind of broken down into the three areas of lighting, marking, and signage, where the lighting is just the appropriate lighting of the runway. But the lighting itself in civil aviation is typically oriented in a way that it tells a story, it sends a message, it tells you about an area. So how are you going to orient lights for incoming or departing aircraft? How are you going to mark areas so that the passenger transfer from the access mode of travel to the passenger processing component is, very clear? So all of these little tiny things we don't pay attention to when we walk through O'Hare or Midway or LAX really drive the circulation, the parking, the curbside loading and unloading, all of the activities that take place in here. So the lighting, the marking, and then the signage itself are key to the flow of the operation. We looked at some of the standards today in aviation in terms of lighting. And as you can see in the table, there's some specific lighting requirements that ensure optimal visibility, safety, and operations during nighttime. There are a few different types of lights that are recommended for various types of operations, such as the in-pavement perimeter lights. They offer, they differ between square and a circle for the fatal areas when you're landing or for a runway. So when you're implementing your vertiport, you have these standards, you're still going to have configuration concerns, but you already have these standards for materials and equipment that you can use. If you're looking for the smaller version, the less power draining version, the more scalable version, you should start from these standards in doing so, and then you'll have a much more safe time with your stakeholder in implementing a newer innovation versus something that hasn't been around for a while. So this particular table, this particular table talks about the key marking requirements. So we take the categories of the requirement, and then we look at building categories beneath each. So we've got the perimeter around the entire takeoff area. We've got the actual landing pad. What's the D value of that? What symbols we're going to use? What's the size and weight of various materials that are being on a location, as well as what they are capable of holding, what type of aircraft can sit there, and the limitations. We look at all of these different things and we plug them in with various aspects after research. So when you think about the vertiport marking, it's the same as kind of, the last slide. You can begin with a number of standards, but you will have to craft those standards to be very specific to the nature of urban air mobility, as well as the nature of the type of vertiport operation in play. So you can't just take marking kit from O'Hare that was used to mark O'Hare Airport and use it for your new high quality airport at your hotel. You need to do something different. And the integration of urban air mobility into the transportation infrastructure already poses those problems. Let's talk about the adaptation of the existing infrastructure. You think about where we're coming from, and we'll say that we are coming from a place like heliports or small airports or even buildings that may be used for landing. There are certain standards that are available to look at today to say this is appropriate according to our regulatory standards, or you need to modify this type of payment to a certain design method or materials method to accommodate the specific characteristic of a specific type of vehicle, such as their weight or different wheel configurations or load distribution or maximum payload. So in that I mean, that's enough right there, right? So a lot of people say, hey, we're going to retrofit our vertiport, which was used for a heliport forever. That approach is going to require the same consideration as building it from the ground. The very same consideration, because there are no vehicles that fit the exact same profile as the existing vehicles or aircraft that land at those heliports or vertiports, as they were originally called. The urban environment itself may require construction of a new vertiport. So in that case, you have a chance to, build those landing pads to support organic UAM operations. So you're building this vertiport organically to support UAM operations based on the best aircraft you want there and the best business model you want there and the best flow of people you want there. So with the pavement itself, now you know from scratch what you need to incorporate into soil investigation, subgrade stabilization, and other pavement materials. We look at green materials in terms of pavement. We want to consider things like photovoltaic, zero feedback type mechanisms that when an aircraft lands, for example, maybe it's giving power back to the local grid. We also want to look at the pavement durability and noise reduction. There are various materials out there that will accommodate that. The question is, does the pavement absorb noise and still lend to long-term durability, especially in places where you're going to have a lot of traffic? And then at the end of the day, these eco-friendly approaches have to really focus on the past concern. So in Chicago, for example, and other cities like it, we have what's called the urban heat island effect. It's really just the city's concrete and other materials which exacerbate the issue of heat being trapped or exacerbate or increased by the pavement surfaces. So here we want to make sure that the materials we use, not only do they not lend to the urban heat island effect, they detract from it. They help the environment. And we're going to want to build these, this infrastructure, this built infrastructure, the pavement itself. We want to build this fast. We want to build this fast. And there are a bunch of reasons for it, but as a standard, innovative pavement design and construction techniques are already being used, with more innovative designs and techniques being explored for their ability to minimize disruption and maintain operational efficiency at airports. Vertiports may be much more, they may have much more traffic. So the concern for building these systems and the ability to deploy these systems, pavement systems, must be fairly seamless and fairly quick, especially if you would have to replace a fatal, for example, for whatever reason. This can't be a year-long process. It must be fairly quick. And then lastly, we have the pavement management system. And the pavement management systems are really just systems that are used to evaluate the pavement integrity, look at the required maintenance schedules for that type of material, and to establish performance metrics that are specific to the vehicles, the business model, and the infrastructure for that facility. Vertiport drainage is also one of my favorite components to talk about, and I can't get enough of this. Now I'll try to tell you why. Vertiport drainage in an airport. If you think about that, if a runway is flooded, or if a cargo area has runoff that impedes the process of moving the commercial asset, that's going to be an issue. So vertiport drainage, akin to airport drainage, is going to be crucial. It's for the safety and moreover for the operation itself. So we wanted to adapt the drainage principles that civil aviation has already taken into account. Not a whole lot of that's going to change. So we look at the space constraints, we look at various capture systems, and various rainfall intensity and frequency patterns. So essentially create an adapted surface drainage system and incorporate a stormwater capture and reuse mechanism into a client resilient design that will also aid in not just reducing that runoff, but potentially reducing pollution, such as oil-water combination. So you may have an oil-water separation process or material in there. You may have sediment traps that will prevent various materials and chemicals from going back into the environment. And you can use other materials that will absorb the water, stormwater, for example, as it enters back into the sewer system or other natural water courses. So, and the last thing we have to do, well, there are two things you really have to do, but the last thing is probably the two things most important. A city like Chicago has a great infrastructure, and we need to coordinate. In the case of drainage, electrical, everything else, we have to coordinate with existing infrastructure. So that existing urban drainage system that has been created for, the example here, 62nd and 6200 South State, that area right there, that drainage system has been maximized for the long term, and it continues to be maintained so that it is efficient in reducing floods and so forth. So we have to coordinate with those municipalities with which we work, whether we're working for the municipality or for our client stakeholder. We have to coordinate and maintain and inspect. We have to have a process in our plan that allows them to integrate with their municipal leadership when it comes to this infrastructure, as well as a recommended process for maintenance and inspection. Now, some of the work has been done already, to be quite honest with you. We know the purpose of the drainage system. And we know that where it will prevent water-related damage, we also want to prevent the actual flooding. So you got a lot of water that can come in, and you need to do something when that happens, but you want to prevent it before it happens. Excuse me. So we want to essentially intercept and then divert the flow of water. And if we identify these things up front, we can prevent the possibility of this type of damage, because the vertiport isn't in a limited space. So if we were to have a flood in that area, it would be problematic, not just for the vertiport itself, but it could truly incorporate damage into the surrounding area. So that's why we want to look at the drainage system. Hold on, almost. And while we're holding, there we go. Okay. All right. So design storm. Design storm is pretty cool. It's a process by which you can hypothesize a other than normal storm. So you essentially use the tools that have been created already, and you take the precipitation patterns from the local climate, add in additional factors such as that urban heat table, rainfall intensity, duration, return period of that type of storm, and you can kind of create this what's called a design storm. So you want to do that for your vertiport location for the obvious reasons. There are it seems to be a huge consideration to develop vertiports in the Florida panhandle down there. And I would imagine that the design storm process, the design storm outcomes are going to be significant in terms of how the built environment is articulated and constructed. It really truly gives you a snapshot of scenarios where erosion, sedimentation, water pollution, all that stuff can be impacted by these heavy types of rains. So you want to look at that, and all those. I don't think I went through all of them. But yeah, there we go. We're good. Okay, so like I said, a lot of this work has been done already. The Army Corps of Engineers have developed a procedure that is just called the rational method that calculates the expected runoff, the volume of runoff, the rate of runoff based on the rainfall intensity and that area in which that water may pool, the watershed area. And then they actually have established runoff coefficients that the engineers may use to factor into the development of airports. So the same approach must be done for the engineers that will be looking to develop the vertiports, the landing zones, the parking areas that are connected. For example, the size and shape of our surface here, I believe we're 19,000 square feet, just our vertiport location. If it floods here, if we know it's going to flood here, we may be able to determine a runoff area just adjacent to it, or we may be able to find a larger drainage system to manage the expected flow. Okay, so the drainage portion is partly solved because the Army Corps of Engineers established the procedures for predicting much of it. It works to the extent that we should still use it. Vertiport Security, this is the most exciting thing for people who are going to spend their money to make money by placing this infrastructure in a place. So let's talk about the various elements we think are important to the airport security. We have a standard vulnerability assessment that we conduct when we look at spaces for vertiports, flight corridors, drone vertistops, and that vulnerability assessment is merely to identify the potential security threats and weaknesses in that ecosystem. Our goal is to really just proactively identify those risks and identify the most appropriate measures that can be implemented in the case of that risk or in advance of that risk to enhance the secure posture of the UAM vertiport, the entire facility, all of the built environment. Making that happen means that we have to look at the ground space of the vertiport. Oops, sorry. The ground space of the vertiport itself. So like I mentioned a moment ago, we've got roughly 20,000 square feet that we need to secure. We need to secure that for the passengers that will be there and the cargo that will be there. So that 19,000 square foot area requires a security model. Again, this is a place where we can kind of rewrite the script and make a security model that is extremely efficient and effective, but doesn't alienate the surrounding community. We also have to look at the ground space for entry into our vertiport area. So we're looking at roughly a quarter mile radius around that airport. And what that does is it looks at the walkways from mass transit, the entryways that are potential into the pathways we may build, as well as safety concerns for blind spots within this ground space. A lot of times you may go to another place in the world, get off that aircraft, walk outside of that facility, and once you're outside, you feel less than safe. And I mean, you know, not the super big city, but we have to look at that area to make you feel safe. The other thing we need to do is look at the vertiport airspace above, directly above. This has to be a secure area for our aircraft to enter and depart. So we have to secure that area with a number of various means. The same means that we use to secure our area just above the airport may or may not be the same area that we will use to secure the airspace, the UAM airspace. So let's say the ground space is at 0 feet. The top of the airspace is at 400 feet, right? So we're looking at the security of the ground, 1/4 mile radius around the ground, the airspace directly above the vertiport, and then that airspace for entry and departure above our airspace, which ultimately is the next level into civil aviation airspace. So the approach suggests that if we can provide ironclad security for people and personnel and cargo on the ground and do the same overhead, and that is those drones that aren't supposed to be there that fly into the zone, that private aircraft that shouldn't be there that flies into the zone, someone that is within the zone, but they are somehow a security threat for the people that are on the way in from an aircraft. How do we manage all this stuff? Really, I mean, what's the method? Well, we have an approach to discover the method, and we have the tools and innovation to deploy the methods that work. So, oh, there's the traditional airspace marker there. So traditional airspace. So 400, all the way here, 400 feet, and then there's a buffer of 100 feet between the top of our UAM layer and the traditional airspace layer. Traditional airspace will be managed by traditional airspace managers. We will not be managing that airspace, we will be monitoring it. To make this happen, our vulnerability assessment goes through a 5-point phase to look at all the assets that we have. So the first step is really to catalog all of the facilities within our environment, the systems, the procedures, the landing zones, the air traffic management systems that are both digital and those hardware components that you can touch, and the maintenance procedures. And that catalog of assets is what we want to protect. So while we prioritize that asset list to show what is most important to us, we can also assign levels of protection for assets that may require a higher level or a special level of protection based on their value or the location or access, or even the impact on the passenger itself. We also need to look at the threat identification. So when we evaluate potential threats to UAM infrastructure, we look at cyber attacks on connected systems. We look at the ability to see other incidents that occur within our environment that could be a potential adversary to our passenger experience or our operation itself. We also go even deeper into the vulnerability assessment to get the specific weaknesses and apply those to another lexicon. So we've got a lexicon of assets that we can identify and weight and protect. And we also have a lexicon of vulnerabilities that we've identified. Now we must continually fix and protect against. So where we have the asset analysis first and the threat second, the vulnerability analysis at this point now spells out the approach for applying solutions. And then we move into the consequence analysis and look at scenarios, really. So we say, based on the effectiveness of our potential system, our recommended system, here's how effective they would be in terms of policies, procedure, the actual protection capability itself. All of these things we go through when we look at the consequence analysis. What would happen to see the potential impact on passengers, employees, even the first responders and the area in general if something did happen and we did apply the measures that we've identified. And then lastly, the countermeasure recommendations. Today, there's a big CUAS movement, so counter drone movement, and that's very important. What are the ways that we're going to prevent unauthorized intrusion? And that means the airspace, the ground space, and the cyberspace. So we will continuously have countermeasure recommendations, and I'm sure the regulatory bodies will come out with some, but they will require constant modification and monitoring. Now, the last piece that we look at is the energy requirement. Excuse me. Now, we know that these aircraft are energy hungry and they're going to save the world. So those are two opposite ends of the spectrum. So we want to look at what were the possibilities available. So we've got charging or energy sources that are connected to the grid. We've got the renewable energy sources, which are just going to kind of be part and parcel of the vertiport location. We've got external systems such that would mirror a battery type storage environment where a VTOL or a drone could recharge. And then of course you have the ability to produce your own power on site. So these are a couple of different blueprints, if you will, or frameworks to consider. But at the end of the day, while these are options that are available, that are standardized, the energy requirement by these aircraft could be significant for a vertiport operator. Let's talk about it, and just really quick. So let's say you've got yeah, let's say you've got an aircraft coming in to charge. You've got two different options today to charge an electric vehicle. So you've got direct current, and then you've got the fast charging version of it. So you've got probably 12 aircraft coming in a day on the medium side of the market when the people start to pick up that this is a great thing, and your aircraft is going to come in at about 10% and need to charge to 50%, all the way up to 90% if possible. So this chart depicts the amount of time it would take to charge based on it being a traditional AC charge or a fast charge, okay? So this is pretty close. You're at 10%, you want to get to 90%, it's going to take you about an hour and a half to charge your vehicle. Now, every vehicle is going to have a different energy requirement and a different profile in terms of what type of energy charger it uses. So what we're going to do is take a snapshot to look at what that could potentially mean. So we used the FAA's Vertiport Engineering Brief 105 reference aircraft battery requirement, along with Archer's Midnight aircraft, Joby's aircraft, and Beta's Alita. And there are some other calculations that we can do here, but we selected Beta, well, we didn't select it, but based on the numbers, Beta is probably the most efficient operating aircraft to design into your vertiport strategy in terms of its maximum flight distance, payload, battery requirement, and charging time. So while it may be 1.5% to charge all the way back up, Beta is a very efficient machine. So that is where we are in terms of built environment. Again, the FAA may change the regulations, but they're not going to change the basics. We're going to design from the basics, and we hope to make recommendations on built environment and airspace, which we'll talk about next week, in the Department of Transportation's RFI upcoming. So join us next month as we move into our second to last phase, phase 4. We're going to talk about airspace design, and our last segment will be vertiport architecture. So where Sandra and I will be presenting you the approach we take to consider and manage and construct an airspace for urban air mobility ecosystem. The last segment will be our requirements gathering based on the capabilities and desires of our chief architect, Giancarlo Zima. And so this should be action-packed, these last two. Thanks again so much for joining us. If there are any questions, please feel to reach out and complete the survey for our next phase. And we'll see you next month. Be safe and enjoy.